right, hello everyone. Today we are going to cover two main topics. We're going to talk about the Lagrangian formalism of electrodynamics. This is going to be a very nice example of how to use field theory to derive equations of motions, to derive Hamiltonian, which will be the basis for all of what's going to follow. And in the second part of the day, we're going to talk about first derive and then use something called Noether's theorem, which you might have heard of. I'll introduce it properly when we get there. This is one of the main results of field theory. What you should note for today is that everything we're going to do is 100% classical. So although you're in advanced quantum mechanics course, and although most of the semester we're going to talk about quantum field theory, today it's going to be 100% classical. Nothing is going to be quantum. There are no operators. There's no commutators. No nothing. So this could actually be a undergraduate like second year course or something, because there's nothing special about what I'm doing. It's just a little bit more involved, and we're really going to try to understand this way to look at physics from a field theoretical point of view. So the basis of any field theory is a Lagrangian, or even better, a Lagrangian density, with which you can build a action. So the action, which is a functional of some field phi, or a bunch of fields, is in general an integral in 4 dimensions, meaning there's an integral over time and an integral over 3-dimensional space, over a Lagrangian density, which is a function of many different fields. So I counts the field number 1, field number 2, field number 3. And it's also a function of its derivatives, d mu phi I, where d mu can be a time or a spatial derivative. So for example, in the case of electromagnetism, the Lagrangian density, as we introduced earlier already, can be built from this electromagnetic tensor f mu nu. This is the part that takes into account all the fields in vacuum, and then there's a second term which couples the fields a mu to the sources j mu, which contains both the charge density, so J0 would be the charge density, and J1, 2, 3 are the 3 components of the current density. And what is this good for? Well, if you have an action or a Lagrangian density, then you can use the Euler-Lagrange equations, and from the Lagrangian derive the equations of motion. So you take your Lagrangian, you take the derivative with respect to the field, phi is called the field, and then you take the derivative with respect to the derivative of the field and derive it again. Note that mu is repeated, so you have to sum over the time derivatives, the x derivative, the y, and the z derivative. So these are actually 4 terms for each field. So if you have more than one field, there are 8, 12, 16 terms. And this will then give you the equation of motion. So in the case of electromagnetism, there are 4 fields. The fields phi I are the potentials a rho. I'm going to use a lower index in the Lagrange equation for today, but it doesn't matter. You may, if you take the same index and lower it in all terms, it's the same thing. It's an overall minus sign, which doesn't make a difference. One thing I want to stress here, and that's very important, as I said, phi is called a field. That is a mathematical description of what this is. In physics, we call A potential. But in math or in field theory, this is called a field, not to be confused with the electric and the magnetic field. So when we're writing down the Lagrangian in terms of fields, what we're actually using are the physical potentials. The physical potential is the mathematical field, not to be confused with the physical field. Okay? You have a question? Yes, this is the Lagrangian density. So the Euler Lagrange equation for the electromagnetic field, I'm going to plug in my fields. So what I have to compute is dou L derivative with respect to a rho, and then minus d mu dou L. Sorry, I'm not going to use mu. I'm going to use sigma, just changing the index. I'll tell you why in a second. And so this is the Euler Lagrange equation for when after I've plugged in the fields for electromagnetism. I have switched to sigma and rho as my indices. Of course, they're dumb indices. I could use whatever I want. And I'm using sigma and rho because I'm going to use mu and mu in the Lagrangian. And I don't want to get confused, so I switch variables over there. So that's that. So what we're going to do now is we're going to compute the first term, we're going to compute the second term, and then we're going to get the equations of motion. What are the equations of motion for electromagnetism? Maxwell's equations, right? So what we expect is that when we take the Lagrangian and stick it into here, what we expect to get are Maxwell's equations. So d mu f nu nu equals j nu. And when we've done that, we'll be able to specify the ratio of C1 and C2. So we'll be able to compare this. What we're going to get, of course, is something that depends on C1 and C2, and we're going to require to have exactly this form, and this way we'll be able to specify the ratio, or at least one of the constants, C1 or C2. So that's our first task for today. So let's start with the first term. That's the easy one. Here I'm taking the derivative with respect to the fields, A rho. The way you probably would do this about half a year ago is you would write out all of the sums, right? You would take rho from 0 to 3 and sigma from 0 to 3, and you'd write out all the terms. And then after you're working with t, x, y, z, it's much simpler and you can do it, right? This thing here with sigma and rho, that's a total of 16 terms. I wouldn't do that. There's a much easier way to do it. It's called field theory. You stick with your indices and just work hard, and you'll get through it. And as soon as you understand the language, it is much easier. So notice that when you're taking the derivative of the Lagrangian with respect to a rho, the first term just vanishes, because f mu nu only depends on the derivatives of the field, not on the field. It's like taking the kinetic energy, which is proportional to x dot squared, and deriving with respect to x, you get 0, because x dot does not depend on x. Same thing here. d mu, right, f mu nu is, let's write it down, d mu a nu minus d nu a mu. It does not depend on a, it only depends on the derivatives of a. So the first term totally vanishes, and all I'm left is with the derivative of the second term, so that is c2, and then there's the derivative of a a mu, which is, there's d a rho, a mu, j mu. I haven't done the derivative yet. I've just cancelled the first part. And I want to take the derivative of a mu with respect to a rho. What do I get? You get a delta function. So this is C2, and I'll explain why in a second. Delta rho mu, j mu. Which of course is just, after you compute the sum over mu, which is just C2 j rho. Why is this a delta function? So this is actually quite simple to understand. It is true for any floor vector. So if you look, for example, of the derivative of the displacement floor vector, so t, x, y, z, dx, let's use, where am I? Dx mu to dx rho. So if mu is equal to rho, this must be equal to 1, because that's like taking dt dt, or dx dx, or dy dy. That's obviously equal to 1. But if mu is different from rho, then this is like doing dt dx, or dy dt. And of course this is a partial derivative, not a full derivative. That must vanish. So you automatically get 0, and this is just a delta function, delta mu rho. Okay? So nice and simple to take this derivative. The second term in the Lagrange equation, that's where it gets complicated. Okay? So let's start with just the derivative of the Lagrangian without the d sigma. So we want to compute next dou L to dou sigma a rho. So let's, before we get into that, let's try and write this f mu nu in terms of a. Okay, so we'll know what we're doing. So f mu nu times f mu nu. I'm going to plug in the definition of f mu nu. So this is d mu a mu minus d nu a mu times the same thing with upper indices. That's d mu a nu minus d nu a mu with upper indices. And now I can multiply, so take away the brackets, so I get 4 terms. I have d mu a nu d mu a nu. Then I have minus d mu a nu d nu a mu. Another minus d nu a mu d mu a nu, and plus d nu a mu d nu a mu. These terms look very similar, but they're slightly different. Of course, they are dummy variables, so you can't switch dummy variables, but you can, if you switch this mu, you also have to switch this mu. You do not have to switch this mu, right? Because each term is independent. So what you see is that the first term and wait a second, mu nu. First and the last, very good, thank you, are the same. Because if I can switch this mu to a mu and the mu to a nu and the nu to a mu, right? Now these are exactly the same, and the same goes for these two, right? If this is a nu, this is a nu, this is a nu, and this is a nu, then these two are the same. So what you get is 1/2 f mu nu. So you get twice, these two terms twice, and I'm dividing by 2 on both sides. So 1/2 f mu nu is d mu a nu minus d mu a nu d mu a nu. Okay, this is starting to look better. Remember, I want to take the derivative with respect to d sigma a rho, so it's starting to look familiar. One more thing I would like to do before I take the derivative is I need to watch out for signs, so minus signs. In order not to get confused, since here I'm taking the derivative with respect to lower indices, I want to turn this into 100% lower indices. So in order to make these lower indices, I'm going to use the metric, what we call G. So I can write d mu with upper index. I can write this as G mu alpha times d alpha with a lower index. And that takes care of the minus signs that are added to the spatial derivatives. And the same thing can be done for the potential. So instead of a nu, I can write G nu beta times a beta with a lower index. So that takes care of these two terms. And then I have to do the same thing for these two, which is exactly the same, just with a nu and a nu, so the other way around. So there's a d nu equals G mu alpha dou alpha, and then a mu equals G mu beta a beta. So after I do that, 1/2 f mu nu is now G mu alpha, G mu beta, d mu a nu d alpha a beta. That's the first term. And the second term is G nu beta G mu alpha d mu a nu and d beta a alpha. So you see, everything I'm doing is very straightforward. There's nothing complicated. There's nothing very physically demanding about what I'm doing. But it looks complicated because there are a lot of indices and a lot of things to take care of. And the trick is be careful. Do it slowly, take your time, get a cup of coffee, maybe two, and you'll get through it. And I've given you some exercises to try it and to drink a lot of coffee. But as soon as you get used to it, it's peanuts. It gets really simple. This will become your second language. Okay, now we're ready to take the derivative. So let's go back to the derivative. The Lagrangian is C1 times twice this thing, right? Because it's C1 f mu f mu, this is 1/2 f mu. So it's 2C1, that'll be a constant that I get outside, and then I have to take the derivative. It was 2C1. And now I have to take the derivative of this stuff over here. Now, I'm taking the derivative with respect to d sigma a rho. And notice that here I have d mu a nu, and then d alpha a beta. So this is the derivative of a product. Right? We know how to take the derivative of product. You take the derivative of the first part times the second part, and then the first part times the derivative of the second part. It's like, you know, kindergarten, just with more indices. Simple, right? So if you take the derivative of the first part, oh, and obviously the g's, they're just numbers. So diagonal matrix with ones and minus ones, it's just a number. So they come before the derivative, they're just constants. So first term is G mu a alpha, G nu beta. And now I take the derivative of d mu a nu with respect to d sigma a rho. This derivative will be equal to 1 only if sigma is equal to mu and rho is equal to mu. Any other case, any other of the 16 options, or well, 4 I already took, so all the other 12 options are all 0. Right? So this is a delta sigma mu times delta rho mu. And then I get the d alpha a beta, because it's a product, right? So this is the first part. The second part, so I keep the constants g mu alpha, g nu beta. I've already taken the derivative of the first part, so now I leave it, d mu a nu. And when I take the derivative of d alpha a beta with respect to d sigma a rho, I get two delta functions once again, d sigma delta of sigma and alpha, and a delta of rho and beta. So far so good? You would all fall asleep, or you've lost me ages ago, or this is really simple. It's very simple, right? It must be the third option. Okay, so now we do this 2 more times. We do the same thing with the second term. So once again, the g's are just constants. That's mu alpha. Taking the derivative, that's delta sigma mu and delta rho mu times dou beta a alpha minus g nu beta g mu alpha dou mu a nu. And now we get delta sigma beta and delta rho alpha. Great. Is it starting to look like Maxwell equations? Not yet. Okay. We'll get there, I promise. So let's just write down what we used. So we used the fact that the derivative of d mu a nu with respect to d sigma a rho is equal to delta sigma mu delta rho nu. Okay, we used this 4 times. Okay, so far so good. Now we can do 2 obvious things. First of all, use the delta function. And second, use the g mu nu and simply go back to upper indices. Right, that'll make it look much more, I don't know, much nicer. So if I sum with over this delta, then the mu's disappear, and all of the sigmas, all of the mu's turn to sigmas. So this goes away, and this sigma, whatever sigma, there are no sigmas, okay, and all of the rows become, here, there's a row here, so this mu becomes a row, and this mu becomes a sigma. Okay, cool. Same thing here. So alpha becomes a sigma. And rho becomes a beta. Here we go. And same thing here. So d sigma mu, that'll give me g, the sigma, and this becomes a rho. And one more, so this delta alpha beta doesn't make sense. I took the derivative, d sigma a rho with respect to beta. It should be sigma alpha, right? Sorry. This is a sigma. See, that's why you need coffee. This becomes a sigma, and rho alpha, this becomes a rho. Okay, that's a good start. Now we can use the g's and go back to upper indices. So again, dl to d sigma a rho is equal to 2c1 times. So now I take over g, so I get upper index d sigma a rho. And from the second term I get d sigma and a rho. Oh, that's interesting. And now I get minus lower index dou rho and a sigma, and minus same thing again, right? With d rho a sigma. So these two are the same and these two are the same, so I can take out the factor of 2, right?
Why didn't you raise the index?
Oh, I was supposed to, sorry, yeah. Sorry. Rho sigma. Sorry, my mistake. So this is 4 times C1. D sigma A rho minus D rho A sigma. Agreed? Does this look familiar at all? This expression in the brackets? This thing, right? This thing here, right? So this is equal to 4c1 f sigma rho. So this derivative is equal to this. Easy to see, right? Just like, you know, one full board of calculation. That's what it's equal to. And it's correct, wow. Okay, so now what do we want to do? So we've computed, right, what was our goal? We started with Euler-Lagrange equations. So we've computed this part, that is over here. And we've computed this part here, just the derivative. That is equal to here. So let's just plug it back in to the Euler-Lagrange equations. EL is Euler-Lagrange. So when we plug it back in, we get C2J rho, that's from up there, minus, there's a minus sign there, and then I have to take the derivative d sigma, so it's 4c1 d sigma times f sigma rho equals 0. Now let's switch back to mu and nu. Again, these are dummy variables, and I'm going to shift sides. So I get d mu f mu nu equals C2 over 4C1 times J nu. I did two things in one. I shifted sides, and I also changed sigma into mu and rho into nu, both in one step. But I think this is the easiest step out of everything that just happened. Okay, and as I promised, what should happen after we apply Euler Lagrange is we should obtain Maxwell's equations. Maxwell's equations. And if you compare what we found to what we know Maxwell equations are, we must set this numerical constant equal to 1, which means that we have found that C2 is equal to 4 times C1. So what we did is we wrote down a kind of a guess to the Lagrangian with some constants which we didn't know, and then we required that they would be, or that it would reproduce Maxwell's equations. And by requiring this, we can fix the constant. Right, that's the general idea. Questions so far? Great. Step number 2, we still haven't really finished with the Lagrangian because we've only determined one of the constants in terms of the other. There's still one constant left. So in order to determine the second constant, what we're going to do is we're going to require another fact that we know. We know that in vacuum, the energy of the electromagnetic field equal to 1/2 integral d3r over electric field squared plus magnetic field squared, where I'm writing E is the absolute value of the vector E, and the same for B. So if this doesn't look familiar, go back to what you know and plug in C equals 1, and you'll get this. Right? Oh, and I was going to tell you, last week I was asked with respect to the units of the electromagnetic field, and I solved it in my head, and I came to the wrong conclusion. I gave you the wrong answer. So in order to make sure you don't walk out of a mistake, it's now in your homework to get the correct solution. Just so you know that. And don't be surprised if you don't get what I said, because I said the wrong answer. The correct answer, it's very easy to find. Just, do it on pen and paper, not in your head. Okay, so this is the electromagnetic energy in vacuum. And what we are going to do now is we're going to compute the Hamiltonian density, which you get by taking the momentum times phi dot, the time derivative of the field phi, minus the Lagrangian, where the conjugate momentum is equal to the derivative of the Lagrangian with respect to the time derivative of the field. Again, this is the Lagrangian density. And then from this we can construct the Hamiltonian, the total Hamiltonian, which is the volume integral over the Hamiltonian density, and we're going to require that this is equal to what we know is the energy of the electromagnetic field, and this way we'll be able to specify C1, and then from C1 we know C2. So that's the second exercise we're going to solve in electromagnetism. Okay, so let's start with the momentum. Of course, this is the case for a single field. If there's only one field. In our case, there are 4 fields. So the momentum, the conjugate momentum, in our case, has an index, which I'm going to call sigma, and then is equal to the derivative of the Lagrangian with respect to, watch out, the time derivative of the field. So this is dou 0 a sigma. And then if you take the derivative with respect to a0, then you get pi 0, which is the conjugate momentum of the field a0. And then if you take the derivative with respect to dou 0 a1, then you get the momentum pi 1, which is conjugate to the field a1. Right, so there are 4 momentums and 4 fields, 1 momentum for each field. Okay? So that's easy. And the Lagrangian, in our case, because we're talking about vacuum, so there are no sources, it's just the first term, C1 F mu nu, F mu nu. So what we have to do is take the derivative of the Lagrangian with respect to dou 0 a sigma. This should look familiar. We just did that for general sigma and rho, but now instead of sigma we have 0, and instead of rho we have sigma. Sorry for the confusion. But that means that the solution is the exact same solution with the same replacements. So this just gives 4C1 F0 sigma. Right? We already calculated that. So what does this tell us, first of all? Let's look back a few pages and remember what F mu nu are and what the different elements are. So you see that pi 0, the momentum conjugate to the electric potential, is the element F00, 0, which is 0, and the momentum that is conjugate, so for I equals 1, 2, 3, or x, y, z, they're the elements F01, F02, and F03, which is minus the electric field. So that's minus 4C1 EI. I guess you could write I with a lower index. There's no real meaning to the electric field in the upper index. It's meaningless. It's a three-dimensional vector. So what do you see from here? So in this theory, and I'm going to try to turn to the analogy of analytical mechanics. In analytical mechanics, the fields are the coordinates, so x, y, and z, and then the momentum is the mass times velocity. It's not necessarily the physical momentum. In many cases, it's the physical momentum, but in general, it's the conjugate or the canonical momentum. So in this case, the fields are the potentials, and you see that the conjugate momentum are the electric field. So electric field has, in some analogous way, the meaning of the momentum conjugate to the physical potentials in electromagnetism. I just note this. There's no deeper meaning, just note that this analogy works. And this analogy also works when you start quantizing the system. So the commutator between a potential and the electric field is like the commutator between a coordinate and the momentum. So this analogy actually continues. And it's something you can use throughout field theory. Okay, so we have the momentum. We would now like to construct the Hamiltonian density. So the Hamiltonian density, again, I wrote it here for a single field, but in our case, there are 4 fields, so we have to take a sum over all the fields. So there's a term pi mu dou 0 a mu. That's this pi phi dot. Phi dot is dou 0 a mu, that's phi dot. Right? And pi mu is momentum. And then minus the Lagrangian density. Now eventually we're going to want to compare this to the energy, which is written in terms of the fields. So it's a good idea at this point to switch the fields and get rid of the potentials, the physical fields, E and B, so that we can compare later. So let's try and figure out what the Lagrangian is in terms of fields, physical fields. So this question is, what is this operator? What is this f mu nu times f mu nu? Notice what you're summing over. So this is, if you stir this for a little bit, you notice it's exactly like the when you do in MATLAB, you do dot times a matrix, dot times this matrix. That's what this sum means. Okay, so f mu nu, sorry, upper index, is like this operation that you do here. It's kind of like doing dot times in MATLAB. Does this make sense? Then you sum over all the elements. You don't stay with the matrix, you sum over all the elements. So go a few pages back into your notes to look up what f mu nu is. Do this multiplication in your head. It's actually quite simple. You get 2c1 minus e squared plus b squared. So now we've written the Lagrangian in terms of the fields, the physical fields. Now let's do the same thing for the first term in the Hamiltonian. So I'm taking pi mu dou 0 a mu. I'm going to write this in terms of fields. So let's write it out. So this is pi 0 dou 0 a 0 plus 4c1 EI, that's the momentum that we found. And then this is multiplied by dou 0 a vector. This thing here is equal to 0 because pi 0 is equal to 0. And we remain only with the second part. And if we now plug these all back into the Hamiltonian density, we have these terms, 4c1 E. So this would be an E vector, not EI. It's a dot product between the electric field and the time derivative of the vector potential. At the moment, we don't really have a way to write this as a field, but we're getting there. So times dou 0 A. And then there's the Hamiltonian, which is plus 2c1 e squared minus b squared. It's minus the Lagrangian, so there's plus and then minus. Okay, now let's do a dirty trick. The dirty trick we're going to do is we're going to add and subtract the same term. We're going to do writing. I'm going to add and subtract 2e dot the gradient of a0 and then do minus this. Okay. You'll see in a second where this leads. So after doing this, we get 2c1 times 2e dot dou 0a plus 2e dot the gradient of a0 minus 2e gradient of a0 minus 2e. I did that. Plus e squared minus b squared. Okay, that's nice. Now we can use the definition of the electric field, namely that it's the spatial derivative of a naught and the temporal derivative of a. So the electric field is equal to minus the gradient of A0 minus D0A. Right, this is well known. This is ddt, remember? So we can now plug this in. You see it appears, what does it appear? Here, D0A, this is 2E, it's the same 2E. So this comes outside, you get D0A plus the gradient of A naught, that's just minus the electric field. So what you get here is 2C1, 2E gradient A0 plus E squared minus B squared. Sorry, minus and plus. Okay, let me explain this. So this thing together, right? This is 2E, and then what you're left with is
Actually, because pi I, you use the first line, there should be a minus sign.
yeah, there's a minus sign outside. Because when you take this, right, this is 2E times this derivative, which is minus E. So this is minus 2E squared. So you have minus 2E squared plus E squared. That's minus E squared. That's this. And the rest just stays the same. So there's a minus sign, an overall minus sign. Okay, now what we have to do is do something smart with this term. So to do something smart with this messy term, what we can do is the following. If you take the gradient of E times A0, what you get is the gradient of E times A0 plus E times the gradient of A0, right? That's just the derivative of a product. But of course, div E is equal to 0 because we're in vacuum. It's equal to the charge density, which is 0 because we're in vacuum. So you see that E dot grad A, which by coincidence, this term, it's not a coincidence, which is exactly this term, is just the gradient of the product, right? It's the same thing. We're almost done, I promise. So this is 2 gradient E A naught plus E squared plus B squared. And now finally, last step, remember this is the Hamiltonian density, and we want to compare this with the actual Hamiltonian, so we have to integrate over all of space. And what happens when we integrate a volume integral over a gradient? What does that remind you of? A very cool theorem that you learned a long time ago. Gauss law or divergence theorem. So you can turn it to a surface integral over E dot A, right? And when you do that, this becomes what we know as a surface term, and it is equal to either 0 or a constant, which you choose to be 0. It's like shifting the energy by a constant. It has absolutely no consequence. So after you integrate over all of space, what we're left with is minus 2c1 integral d3r. The first term vanishes because it's the boundary term, and we're left with e squared plus b squared. Okay, so we're done. We can now compare the Hamiltonian to the energy. And when we compare this, we see that minus 2c1 needs to be equal to 1/2 for our theory to work. And we have thus found that c1 is equal to minus 1/4. And now we can also plug this back into C2, and we can evaluate C2. It's gone by now. But we can also plug this back in and find that C2 is equal to minus 1. And therefore, the Lagrangian density is equal to minus 1/4 F mu nu. F mu nu minus A mu J mu. And maybe one more thing you should note here, this is in SI units together with, of course, h bar equals c equals 1. If you use Gaussian units, which some people do, I think Efrat does, you get all sorts of 4 pi. So I think there's a 1/16 pi here in that case. You get 4 pi's everywhere in Gaussian units, which is why I hate them. So this is in SI units, and this is a form that is very well known. At least the first part, minus 1/4 F mu nu, appears everywhere in field theory, classical and quantum field theory. It appears in what's called the standard model. If you've heard about that, it depends how you write it, but pretty much one of the first terms in this page-long Lagrangian called the standard model. So this is the very first term that you find there. Okay, questions so far? Shoot.
You lost the divergence of the E dot AFS because of the boundary conditions?
Yeah, when I take the volume integral. When I take the volume integral over the divergence, then I get a surface integral. So instead of a integral d3 over this gradient, I get an integral d2r over the surface, and I choose the surface obviously at infinity, right? And by this, well, this is actually an assumption. I'm assuming that nothing is entering from infinity and going out of infinity. If you're okay with this assumption, then all this does is it's a constant, right? Or it's actually 0 because there's no flow across. Right? It's Gauss theorem, so we have to assume there's no flow across the Gauss surface, and I'm assuming that nothing is flowing into infinity. If you're okay with that assumption,
So nothing just appears or disappears.
Correct. Correct. That's what I'm assuming. Are you okay with that?
Yeah.
I mean, it could be wrong, but physicists usually.
Well, now there's no reason to.
Exactly. Physicists usually assume this to be true, and actually there's a whole field of research where people assume that this is not correct and then try to figure out what's going to happen if this is not correct. So yeah, some people are really bored and they do that. But in general, this is what we assume. Okay, any other questions about Lagrangian before we continue to Noether? Okay. So before I derive Noether's theorem, I'd like to give a motivation. So this has to do with the connection between symmetry and conservation laws. It is a very deep and quite profound property of nature, of physics, that for every conserved quantity, say energy, momentum, charge, there is a symmetry of the system. I'll define in a second what I mean by symmetry. And also the other way around. For each symmetry, there is a conserved quantity. And Noether's theorem gives you a way that if you know the symmetry, then you can find the conserved quantity. That's what it does. So you might have heard about the fact that the symmetry under time translations leads to conservation of energy. So if your system is invariant under time translations, which in general language means it's the same today as it will be tomorrow, the system behaves the same, then energy is conserved. Or if you run a video forwards and run it backwards and it looks the same way, then energy is conserved. If it doesn't, then energy is not conserved. What this means in physics is that if you take, so let's look at time translation. Time translation means that instead of t, you plug in t prime, which is equal to your time t plus some constant or minus some constant. If the equations of motion do not change when you replace this, then they're symmetric under time translations. Okay, so you do this translation, and what happens is equations of motion do not change. That means that the theory is symmetric under time translation. And of course, if the equations of motion do not change, that means that the Lagrangian doesn't change. That means the action doesn't change, and so on. This is what we're going to use now. So what I'm going to do is I'm going to demonstrate as a motivation, I'm going to show you that gauge invariance, so we're back in electromagnetic theory, so gauge invariance leads to conservation of charge. You heard of this property before? Some of you may have heard of it before. It's a very deep connection. Back when I used to teach electromagnetic theory in third year, I used to show this as part of third year course, but I'm not teaching anymore, so I show it here. So what does this mean? First of all, what is conservation of charge? What does that mean? How can I mathematically express conservation of charge? So what I need is a continuity equation. This is the continuity equation, and this expresses conservation of charge. There will only be an accumulation of charge at a certain point if the current changes at that point, right? It's like when you're driving on the motorway and 2 lanes go into 1 lane, so your current is changing. You used to have 2 lanes, then you have only one lane. So at that position, all the cars accumulate, right? So that's what this equation means. And a gauge transformation means that I'm taking the fields, or the mathematical fields, which are the physical potentials, and I'm going to replace them with a mu prime, which is equal to a mu plus the foregradient of some arbitrary function, which I call gamma. So I'm going to show that invariance or symmetry under this transformation leads to this equation. So let's write down do this properly. So I'm going to form 2 actions. I'm going to form the action that depends on the fields A mu. I am then going to form an action which I call S prime that depends on the fields A mu prime, so which is equal to the original A mu plus this transformation. And then I'm going to require that these 2 are equal. And when I require that these 2 are equal, that will lead to this equation. So let's start with the Lagrangian. It's minus 1/4 f mu nu minus a mu j mu. And this is equal to, repeating some of the math we did earlier, it's minus 1/2 d mu a nu minus d mu a nu d nu a mu. minus a mu j mu. Excuse me? So what I'm trying to show is I'm building one action by using the fields a mu, these fields, the original fields. I'm then going to write a different action that depends on the primed fields, which are defined as I wrote here. So we get a different action because using different fields, right? It's now a mu plus d mu gamma. And then I'm going to require that they are equal to each other.
No, I understand. Why do you use the prime over S? A mu, it's not an...
Yes, but I want to stress the fact, I guess you don't really need it if you don't want to. But I'm trying to stress the fact that this S prime is a function of A prime. Okay, so I'll be able to leave out these brackets and you'll still be clear what I mean. It's just a convention. But it's the same functional form, of course. Okay, any other questions? Okay, so this is the Lagrangian. I did a little bit of math, which we did earlier already. So now let's write, again, this is your question, writing L prime, which is just the same Lagrangian, but in terms of the primed coordinates. It's the convention I'm using. So we get minus 1/2. Now everywhere where I wrote A, I have to write A plus the derivative. So it's minus 1/2 d mu A nu plus d nu gamma d mu A nu plus d nu gamma minus d mu A nu plus d nu gamma d nu A mu plus d mu gamma, and one more, minus A mu plus d mu gamma times j mu. Okay, that was a very simple action. Just replaced A by A prime and plugged in this transformation. Now this looks more complicated than it is because a lot of the terms here disappear. So in the interest of time, I'll skip a little, but basically what you see, maybe I can show this to you. So if you look here, there are a lot of terms here. Okay, I'll let you show this as an exercise at home, but basically what you can show is that L prime is equal to the original L, and there's only one small addition, which is d mu gamma times j mu. Everything else either cancels, and whatever doesn't cancel, you will find is exactly this term here. And the only term that does not cancel is this term. It's a little bit of math. You open up the brackets and you cancel terms, and the only property that you have to use is the fact that partial derivatives, the order doesn't matter. So you have to use the fact that d nu times gamma is equal to d mu gamma. The order is irrelevant. Right, this is a well-known property.
Should be up.
This one's up, yeah. Another one?
Yeah. Below.
Where am I?
The second term. Below it.
Yeah, this is supposed to be upper index. So after 7 o'clock, my brain isn't working anymore. Yeah, sorry for that. Lower than upper. Good, perfect. So using this simple property, it's just a matter of writing out the terms and you'll get this form. Now this means that the old action, which is integral d4x L, which I require to be equal to S prime, which is integral d4x L prime. This is what I'm requiring. Because if the action is unchanged, that means that the equations of motions are unchanged, and that means that electromagnetism is invariant under this transformation. So by requiring that it is invariant, the only thing that doesn't drop out is this term here. So the only thing that remains is integral d4x d mu gamma times j mu equals 0. Right? Because the L part, which is the same L on both sides, just cancels, and this is what I'm left with. And this has to be satisfied for all gamma. Right? Gamma is an arbitrary function, so obviously gamma equals 0, this works, but also for gamma, any arbitrary function of time and x, y, and z coordinates, this has to be true. So how do I do that? How do I take a derivative of an arbitrary function? Hint, it's inside an integral. Integrate by parts, right? So I can move the derivative from gamma to j mu. So this is like saying integral d4x times gamma d mu j mu is equal to 0. And there's the surface term, which is irrelevant because, again, I'm assuming that there are no currents coming from infinity. And we agreed that that was a valid assumption, right? So by assuming that no current is, or no charges are entering into our universe from infinitely far away, there's this first term vanishes. Now there's a minus sign here, which I don't care about because it's equal to 0, and I get this equation. And this, of course, is true if d mu j mu is equal to 0. And now by writing this out, you will notice that this is exactly this equation. So d0, j0, if you want, is equal to if j. Made a mistake here with indices again. Upper index. When you do this sum, there's no minus sign on the left-hand side, because remember that the dou is the opposite of the j's, with the minuses. So all have plus signs. When you shift one to the right-hand side, then you get the minus sign here. Of course, you can now from here obtain or that's in our notations, dt rho equals minus dt rho equals div j vector. And if I now integrate over all of space on both sides, then what you get is that d dt over the integral of rho d3r is equal to, again, we're using the same thing again and again, volume integral over the gradient is equal to a surface term over j, nothing's entering, equal to 0. This thing is what we call the charge, so what you see is that dq dt, q is the charge, is equal to 0, which is, again, conservation of charge. This is the global conservation of charge, so all of the q in all of the universe together, time derivative is equal to 0, and this is local conservation of charge. If you look at point r at time t, then if something enters, that means it accumulates. Confused? This is the same equation, but this is looking from the outside onto the entire universe, and this is looking locally at a specific point. But you see that the same equation, all you have to do is integrate and use the divergence theorem. Okay, so just to recap once more, the conservation of charge is the direct consequence of the equations being invariant under gauge transformation. Of course, this doesn't surprise you much, but imagine that you would be able to guess a Lagrangian for some theory, some nuclear complicated theory of what's going on particle colliders. And for some reason, you're able to guess a Lagrangian, and then you discover that your Lagrangian has a symmetry which you did not intend to have initially. You suddenly notice that it has a symmetry. That means you have now discovered a conserved quantity that you did not know of beforehand. And this has been done multiple times in history, so it's actually quite a nice thing to know and do. So now I'm going to derive formally Noether's equation. Do I have time for it? Hope it will last. I'm going to derive Noether's equation, and then I'm going to apply Noether's equation to time translations and space translations, and to get conservation of energy and momentum. And then you'll be able to apply these theorems at home various times again and again. Okay, cool. So, Noether's theorem. Let's go for it. Again, this is all classical. Okay? Stressing the point, this should have been taught 3 years ago. So I'm going to consider a very simple case. We're going to have only one field. Only one field. We can generalize later. I'm going to call it phi of x. And there's some symmetry transformation under which this field phi of x becomes a different field phi prime of x, right? A mu became a mu prime, so this is now phi becoming phi prime. Think of this transformation, for example, of shifting x to x plus a. And under this transformation, the field changes by f prime, and f prime will be equal to fx phi of x, or the original field, plus alpha, which is an infinitesimal parameter, times some change in the field, delta phi of x. So this is infinitesimal. This is the change in the field. It's not delta times phi, it's one variable. Delta phi is one variable, and it is the change in the field. And I'm assuming here, when I'm doing this equals, that the translation is infinitesimal. So instead of doing a space translation from here to Australia, I'm using a very small baby step, and if I want to get to Australia, I just do 1,000,000 baby steps, right? So I can always look at the infinitesimal case, and it's the same as looking at the general case, just have to do it 1,000,000 times, right? So the infinitesimal transformation leads to approximately the same field. The only change is some small number times a function which describes this change. In addition, now this transformation leads to a change in the Lagrangian. So the Lagrangian will become a different Lagrangian, which again can be written as the original Lagrangian plus some infinitesimal parameter times the delta L, which is the change in the Lagrangian. And since the Lagrangian is a function of the field phi and its derivatives with respect to time x, y, and z, that means that the change in the Lagrangian, I'm just going to use the full derivative, it's equal to dou L dou phi times delta phi, the same delta phi we had up here, plus dou L dou mu phi times the derivative dou mu of delta phi. That's just a total derivative. as you learned first year, I think second week of your math course. Now, this expression can be simplified. Remember that all of this has to appear actually appear inside the action. So there's an integral d4x over all of this, which means I can integrate this by parts. And of course, I get a surface term. So when I integrate this by parts, we get that delta L, the change in the Lagrangian, is d mu times dou L. This is the surface term. Dou mu phi times delta phi. Plus, and then we have dou L, dou phi minus d mu on dl dou mu phi times delta phi. This. When you integrate this by parts, you get the derivative of the product, that's this part here. And then you get minus the derivative of dou L times delta phi. And that's this term. And now you should go, aha! Because what is this? Lagrange, it's equal to 0, right? So the change in the Lagrangian is equal to this expression. And since this is a boundary term, and you then, so the change in the action, the difference between S and S prime, is equal to the integral d4x over the change in the Lagrangian. And since this is a surface term, once again, divergence theorem, blah, 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 equal to 0. So this indeed is a symmetry transformation. Now, how can we apply the theorem? Let's state the theorem. So before I told you that the action does not change under a symmetry transformation. Of course, it's not entirely true because the action can change as long as it only changes up to a boundary term. If it changes up to a boundary term, basically shifts by a constant, then the equation of motion, when you do Euler Lagrange, the constant is going to vanish. So if the action changes by a constant, the equations of motions are still invariant. And that means that the Lagrangian is allowed to change under a symmetry transformation, but at most by a four divergence. So L is allowed to become L prime, which is equal to this infinitesimal parameter alpha times d mu, and I'm not going to use capital J mu, where mu again is an arbitrary function. If the Lagrangian changes by this, then the action only changes by a surface term, which is irrelevant for equations of motion. So even though the Lagrangian does change under a symmetry transformation, if the change is only this, it's okay. It's still a symmetry transformation. Now we can equate the two delta L's. So this is the change, and this thing here is the change, delta L. So by equating the two, we find that d mu times dou L dou mu phi delta phi is equal to d mu capital J mu. And this is actually already is Noether's theorem. Let's just write it in a more convenient way. I'm now going to define what's called the Noether current. J mu of x if you want, where x is a 4 vector. Is equal to dou L dou mu phi times delta phi minus J mu and you then see if this definition, Noether's theorem, is that d mu J mu, because that's what's written over here, is a d mu, right, is equal to 0, and you recognize this. This is a continuity equation. Which means that the conserved charge, or the Noether charge, is the integral d3r over the 0 component of this charge. So how is this theorem applied? You start off with a Lagrangian. Lagrangian is given. You know your Lagrangian. For example, f mu nu, f mu nu. You then think of a symmetry transformation, and you check that under the symmetry transformation your Lagrangian does not change. And if it does change, it only changes by a derivative of some function. So you find this capital J mu could be equal to 0, could be equal to whatever. You find how the fields change, delta phi, plug into this equation. Now you found Noether current, and if you integrate the 0th component over all the volume, you find the charge that is conserved. Could be energy, could be momentum, could be isospin and all the weird nuclear stuff. This is how these things are derived. So in the last few minutes, which I hope I still have, is this clear, by the way? Questions about this derivation? Did I lose you? Looks like I lost like 90%. Okay, so for those who got lost, this is a formula. They don't teach you like in engineering classes. This is a formula. We can plug into the formula. Okay? For the physicists, this is what it means. Okay? And I'm going to apply this to find what's called the energy momentum tensor, which is a complicated word, but basically means we're going to show that energy and momentum is conserved if your theory is invariant under time and space translations. So the translation, the deformation of the fields, or the symmetry conversion that we're looking at, is taking the coordinates x mu, so time x, y, and z. We turn them into x prime mu, a new coordinate, which is equal to the original coordinate x mu plus or minus a mu. And a is a constant, or it's 4 constants. We're shifting in time, in x, in y, and in z. We're not rotating, we're moving in time, moving in x, moving in y, moving in z, in a straight line through space-time. Okay? And we're going to show that this means that energy and momentum are conserved. So let's do the first step first. Let's see how our fields deform. So phi of x, I'm doing this for a general Lagrangian. I'm not going to write down a specific theory. You'll have the chance to do that at home with your huge mug of coffee. We're going to see how these fields transform. So phi of x becomes phi prime of x prime, which is equal to phi of x minus a. Sorry, plus a, because if you move coordinates back, it's like evaluating the field forward, right? When you drive forward, the trees go backwards, right? So that's what happens. And if a is infinitesimal, when this a is this alpha, you can do, as I said, baby steps, and do 1 million of those, you'll get to Australia in the end. I mean, more than 1 million, but, right? So if a is a very small parameter, you can expand this in a Taylor series. So this is equal to phi of x plus a mu d mu phi. It's just the first term of a Taylor expansion, right? For small a. The next term is 1/2 a mu, so it's squared, and 2 derivatives. But it's infinitesimal enough that we only use the first term, and that means we've already done the first step. We have found our delta phi. This here is delta phi, right? Compare with this form here. There's an infinitesimal parameter, and this is delta phi. It's delta phi mu because we're looking at 4 changes at once. I'm running late. Okay, let's see how the Lagrangian changes. So the Lagrangian, the same thing happens. So Lagrangian becomes the primed Lagrangian, which is equal to the original Lagrangian plus a mu d mu L. Now remember that the Lagrangian, again, I've simply done a Taylor expansion. And remember that L is only allowed to change by the derivative of some function. Here. And we're not quite there yet because there's no mu here. There's just an L, and we need to get a mu there. So what we can do is we can use a delta function. This again, it's a cheap trick. It looks complicated, but it really isn't. So I can write this as a mu d mu delta mu mu L. After contracting mu, you're back where we started. And a delta is just 1. I multiplied by 1. Right? That's what I did, just in a weird notation. But all I've done is multiply by 1, by the identity matrix. And that means that this thing here is our capital J. Mu. Okay. And now we can plug delta phi and J mu into our formula, which was written in the book, and we don't care how we got to it. Right? So we have the Lagrangian derivative. So as I said, we're not going to do a specific example, but if you know your Lagrangian for some theory, this part is easy. We've done it 3 times today already. And now you found delta phi and J mu, so you can plug it back in. So let's do this. I'm almost done. About 3 minutes, I'll get to the bottom line. Which is going to be the wow effect. So now the netter current, I have to use a slightly different notation. So it used to be J mu, where mu just are the different terms here, right? It's the time-like component and the space-like components. That was for one transformation. Here, in addition, there are 4 different translations. So there are 4 currents which depend on t, x, y, z. So 4 currents that depend on 4 coordinates. So mu are the coordinates, and the 4 transformations, I'm symbolizing them by lower index nu, which by the way means I'm going to have to switch indices here. Is going to be d mu phi. And the same goes for, no, j remains mu, but there's a nu here. That's the nu I need. So this is going to be equal to, Noether's theorem, the derivative of L with respect to the derivative of the field times delta phi, which is d mu phi, and minus j mu, which is this delta function, so it's minus delta mu times the Lagrangian. And only one last step, I'm going to take the mu as an upper index, and instead of using j, I'm going to use t. That's just a convention. So this is dou L dou mu phi times d mu upper index phi minus delta mu nu L. And this t is what we call the energy momentum tensor. It is called a tensor because it's a 4x4 matrix. Both mu and nu run from 0 to 1. So going along nu, which is along the rows, tells you the conservation laws for different transformations. Top row is for translations in time. Second row translations in x, then y, then in z. And if you go on the columns, it's the in the continuity equation, the time-like component, the x, the y, and the z component. Okay, so there are 4 continuity equations. These continuity equations that express the conservation of charge, or some charge, of a Noether charge. Noether charge. We use the name charge from electromagnetism for any conserved quantity. So that is expressed as d mu t mu nu equals 0. So you sum over mu, and you have 4 equations. Mu equals 0 is what we're going to find as conservation of energy due to time translations, and then mu equals 1, 2, 3 are conservation of momentum due to translations in x, y, and z. Right? And mu is the same coordinate that we've had all along. So don't be confused by this double notation. Now what about the conserved quantities? Let's go back to Noether charge. So we plug in mu equals 0 on j, or which we call t now. But of course, there are 4 conserved charges. So q nu, these are the 4 conserved charges, are equal to integral d3r on t mu equals 0 and nu. So we only care about the first column in this matrix and integrate the 4 quantities in the first column. So let's just do this. Last 2 lines for today. So q0 is integral d3r t0, 0. So let's plug this in. So t0, 0, this is it, so it's dl d0 phi. We're about to have a wow moment. So does this look familiar? It's the conjugate momentum. Remember about 60 minutes ago? Sounds like a long time, right? It's the conjugate momentum, so it's the momentum times phi dot minus Lagrangian. That's the Hamiltonian density. This is integral d3r Hamiltonian density equals Hamiltonian. So q0, the thing that is conserved under time translation, is the Hamiltonian. Pretty cool, right? Okay, and what about translation in space for I equals 1, 2, 3? So it's the integral d3r t0i. That's the integral d3r dou L dou 0 phi dou I phi, and no Lagrangian because there's a delta here. And remember, we plugged in mu equals 0. So if mu is 1, 2, 3, this just drops out, and it's just this part. And so again, we get the momentum. So this doesn't look as familiar, maybe, but this is what you should know as your momentum. And one last thing I'd like to stress is that this is the physical momentum, so mass times velocity, whereas pi is the momentum field conjugate to phi, the original field. So this pi is not a physical momentum. The physical momentum that you measure is this quantity, and it's defined this way. You might remember in one of your electromagnetism courses, you spoke about momentum of a magnetic field, of electromagnetic field, and you saw that it was proportional to the Poynting vector. Remember a bell? Ring a bell. So in your homework, you will apply this equation to the Lagrangian of electromagnetism, basically using pi and phi from electromagnetism, and you will show that this is equal to the Poynting vector. You will get E cross B. So this is, a year ago, people just told you that was the momentum. You didn't know where it's coming from. This is where it comes from. This is what momentum means. So you should stop thinking about momentum as mass times velocity. You should start thinking about momentum as the quantity that is conserved under translations in space. That's what momentum means to a physicist. You have to run 3.5 years to get there, right? It's really messy. Okay? Questions about this? Okay, great. So I'm going to upload the homework exercise. There's going to be an exercise every 2 weeks, so after every tutorial. And it's like 7 or so in total. Did Efrat talk to you about grades of the homework? No, so maybe I should do that. The homework is not graded for right and wrong. We want you to work and to work hard. But we're not going to punish you for making a mistake because you're supposed to learn from your mistakes. So first of all, you'll see in a lot of the homework exercises, you just have to show that and the solution's already given. So you'll be able to play around until it works. You will get a grade for handing in your homework on time and for trying everything. So if you hand in your exercise too late, then I'll take off points. And if you only tried half of your exercise, then you only get half of the points because you only tried half as much. But if you try everything, even though all the solutions are wrong, I don't want to encourage you to get wrong solutions, try and get the correct solution. But even though it's wrong, don't be afraid of making mistakes because you're not going to punish for that. So just make sure you're doing it. You have 2 weeks, it's a long time. So that's that. Questions about the homework? Great. So I'll see you in 2 weeks.